Hello and welcome back to Yeyu Lab for another multimodal tutorial. This time, instead of diving into a cloud-based API like Google's Gemini 2.0 Multimodal Live API, we are switching gears to another similar stuff but built on a completely different tech stack. We're talking about a fully open source, local deployed multimodal assistant that combines with Whisper for automatic speech recognition, Q1 2.5 for multimodal generation, and Kokoro for text-to-speech task. This project really marks a significant shift away from relying on external API services, moving towards a solution that's more customizable, private, and potentially more affordable. In my early tutorials, I demonstrated what you can achieve with the Gemini Multimodal Live API by creating interactive chat applications that handle real-time audio and images. We built a Next.js serverless chat app, a screen sharing app, and even mobile version for Android app. I also point out that some of the current limitation of the Gemini, since it's still in experimental status. For example, you can see there is maximum session duration, which is limited to up to 15 minutes for audio and up to 2 minutes for audio and video. And you can also find that for the rate limits, there are 3 concurrent sessions per API key is allowed. So this means currently it's not ready for massive usage. But our new demo project in this video will directly address those limitations. While it may not yet match the raw performance of this top-tier integrated Gemini model, it brings some pretty compelling advantages to the table. Okay, let's quickly see the demo. So this is the front end that I newly designed for all this multimodal live demo, including the Gemini version or the open source version. And it's designed in Vite framework and React, and based on the language of TypeScript. So let's start screen sharing. Let's share the Multimodal Live API page. Hey, what do you see on this page?
This page shows details from Google AI for developers regarding their Gemini API documentation, specifically focusing on capabilities like voice activity detection, VAD, token count limitations, rate messages events, among other features related to multimodal live APIs. It also includes sections explaining how sessions work with text generation models in real-time interactions.
Can you quickly explain the rate limits?
The Multimodal Live API has 2 main rate limits. It allows for up to 3 concurrent sessions per API key, and there's an upper limit of 4 million tokens processed per minute across all requests combined.
Now let's try a different language, maybe Chinese. I choose a voice called Xiao Xiao. Let's see how she speaks. I will choose to share a Chinese language newspaper.你能描述一下今天的重要新闻吗？
今天的头条新闻包括中国定5%左右目标以应对贸易战，以及李强提完善两岸经济文化交流合作政策。此外，还有一些国际和国内的热门话题，比如美国可能与加默达成折中方案，美检察官针对黑客攻击案提起诉讼等。你有兴趣听更多细节吗？
And we can also test its capability of understanding shape and objects instead of the words and the characters. So let's try to solve a math problem. Let me share a math problem. Hey, can you calculate the area of this triangle?
To find the area of the triangle shown in the image, use the formula area equals base height / 2. Here base is 4 units and height is 8 units. So calculate it as area equals 4 * 8 / 2. Let me know how much I should fill into the box.
So how much?
The area of this triangle can be calculated using the formula / text area equals / frac12 / times / text base / times / text height /. Here it would be / text area equals / frac12 / times 4 / times 8 equals 16 /. So the answer should be * 16 square units. Is there anything else you'd like me to explain?
It's pretty much good, right? So I want to repeat what's the advantage of such open source projects. That's first of all, there are no rate limits and fees. You know, there's no session limitation or rate limits for the usage within the scale of your GPU resource. And then there's a customization and extensibility advantage, right? You want to add support for Japanese, Spanish, French. That's very easy to switch. Or maybe swap out the image recognition from QN to any other new model. It's all straightforward to be implemented. And let's not forget about the data privacy. If you are working with sensitive information, keeping your data local is the key. Now I want to emphasize that it isn't about replacing the cloud API entirely. This is more about exploring an alternative solution for those who want to great control, flexibility, and privacy in the multimodal real-time agent. So how does this system work? Let's see the system diagram. It functions as a 3-stage pipeline, which each stage managed by a dedicated open source model, including Whisper Small for transcription, or called STT or ASR, and QN 2.5 VL7B instructor model for multimodal text generation, and the Kokoro model, which is for TTS processor. The whole process is coordinated by a WebSocket connection, which allows for real-time interaction with the client. So let's break down the key components and the workflow. So first, the client browser, which is not the focus of this video, but you have already seen in my demo that it captured the audio and video data using standard web API and sent the audio data in PCM and video data in image JPEG encoded as a base 64 through the WebSocket to the server. And the WebSocket server built with Python is managing the WebSocket connection, handling the audio segmentation, and coordinates the 3 test stages. So before go to the model, first we have an audio segment detector. This is a very important component to analyze the incoming audio stream of the speech activity. It uses energy threshold and silent detection to pick up the meaningful speech segment, ensure the system does not waste time and the resources for processing continuous noise. And then the Whisper transcriber to convert the detected speech segments into the text, and this text will go to the QN 2.5 model. And the QN 2.5 model will also accept the data from the WebSocket server directly for the image data. It will combine the text and image data to do its text generation. And then the generated text is fed to Kokoro TTS processor to generate the synthesized audio and send that audio data into the WebSocket server again. The WebSocket server will send this audio in base 64 format to the client to make the audio playback by the client speaker. Now let's talk about the WebSocket API. The goal here is to make it fully compatible with the Gemini Multimodal API so that existing client apps like camera chat or screen sharing can still be reused. So here is a quick rundown of this API structure. The first is the config message. So when a client connects, it should send a config message for initial. So although the server doesn't currently process the content of this message, it's best practice to send an empty JSON object for future compatibility. And then is the send message. It will send the audio and image data wrapped in a JSON object under the real-time input media trunks and with a MIME type. So this is fully compatible with the current Multimodal Live API from Gemini. Oh, make sure that the audio data should be base64 encoded audio PCM, which is 16-bit, typically at a 16K Hertz sample rate. And then the receive API, that's to send the audio data from server to client, only including one key audio with base64 encoded audio data also, but even it's with base64 encoded audio data with 16-bit PCM. But you should be careful that it's typically at a 24K Hertz sample rate, because we have to be aligned with the Gemini's Multimodal Live API. So this data will be needed for the front end to plate it back. Now let's go a little bit deeper through some of the key functions within the Python server code. Remember, the full source code is available on my GitHub repository in the description below. So I will focus on the core logic and abstract away those less critical details. So you can find in my code base to see what packages need to be installed, including the transformers, the WebSockets, the Kokoro, and the pillow and other things. So the first class you see is the audio segment detector, which is the first stage of our process. This class is responsible for identifying speech segments within the continuous audio stream, especially the add audio function, which is the core of this detector. It receives raw audio data, calculates the energy level, and implements the logic to detecting the starts and stop of the speech segments based on the threshold and the silence duration. Here the TTS playing and TTS lock are used to prevent processing audio while the TTS is playing. This is a temporary mechanism to avoid an audio loop during response playback. And get next segment is the function that retrieves the next available speech segment from an internal queue, segment queue. Then we have the first model in the workflow, defined in the class Whisper Transcriber. This class handles the speech to text, or called ASR, conversion use OpenAI's Whisper model. So Whisper has a family from tiny to the large model, depending on their performance and efficiency. And I choose Whisper Small here, which is enough for our job here to think about the balance. So importantly, Whisper supports multiple language, which makes it a best choice for diverse global market. To use Whisper within the Hugging Face Transformers library, you will need to install the Transformers Accelerate and Bits and Bytes to make the pipeline function fully work. The most critical function in Whisper is the transcribe function we defined for taking the raw audio bytes, converts them to a NumPy array, and uses the Hugging Face pipeline to perform the transcription. By defined task transcribe language, you can define as Chinese or English or other language. And then we move to the QN multimodal processor, which is the second model lies in our workflow. This class manages the multimodal generation using the Q1 2.5 VL model. And we can select the 3B or 7B model for this generation. But here I think 7B is more accuracy and well performance to this task. We selected Q1 2.5 VL 7B instruct with a 4-bit quantization by using the bits and bytes config to reduce the usage of our GPU resource. The Q1 2.5 VL model is very capable of visual understanding, including object recognition to analyze the text, charts, icons, and layouts within the images, which exactly aligned with our expectation for a multimodal reasoning backend service. And the 7B model is very efficient in GPU resources. So there are two critical functions: set image, which caches the most recent image received from the client, uses an asynchronous lock for the safety of thread, and the generate function, which generates a response based on the provided text and cached image. It constructs a prompt using the processor's chat template, ensure the model understands the conversational context. Here we will use the model for voice interaction. So in the system instruction, I ask the model to keep the answers concise, fluent, and conversational. Use natural oral language that's easy to listen to. So it's very critical because we don't want the model to speak very detailed in response. Then we move to the last model, Kokoro, for the TTS processor. You may have heard about Kokoro. It's a lightweight open source TTS model with only 82 million parameters. So compared to the much larger models, the performance is very compatible. And the most important is the Kokoro supports multiple language and voices. For example, we can utilize the LAN code in its pipeline to use Z for Chinese, or A for English, and E for Spanish, and a lot of other language can be defined here. And also you can select a different voice based on different language. You can find in its Hugging Face page the voice page to see voice you want to pick up. So look back to the code. The most critical function is synthesized speech, which converts the given text to speech. In its pipeline function, we also need to provide the split pattern, which is very crucial for generate natural speech by splitting the text into smaller chunks based on the punctuations. Here I add the Chinese punctuations and English punctuations to make sure the voice speaking is very natural. Then we have our main function that handles the WebSocket connection with the client. We have the send keep live, which will send periodic ping messages to maintain the WebSocket connection. We have the detect speech segments, which is the call processing loop. It continuously retrieves speech segments from the audio segment detector, transcribes them, use Whisper transcriber, and generates response using the Q1 multimodal processor, and synthesizes the speech using Kokoro TTS processor. The result audio is then sent back to the client side. The TTS playing flag is managed to prevent overlapping TTS and speech detection. And we also have the receive audio and images function to listen for incoming messages from the client, including the audio PCM and image JPEG. It passed the JSON payload to extract them and passing them to appropriate processing functions. And use the async IO gather to gathering the receive audio and images, detect speech segments, and keep alive function into a group to be run concurrently. After all these classes and functions are well defined, we can build server and bring it up. Here we initialize all the instances of the processors and start the WebSocket by using this WebSocket server function. And we define the IP address is 40 that indicate the WebSocket server to be published externally with a port 9073 and other settings. Now we have the server ready. To experience this multimodal assistant server, you can simply clone the GitHub repository to download this man.py file, install the dependencies, and start the server by directly running this file. So let me remind you that this entire multimodal service requires a GPU with at least 70 GB of the VRAM. So if you already have a machine equipped with a suitable GPU, that's fine. You can run the server directly on your existing hardware. However, if you don't have access to such a machine, a cost-effective alternative is to rent a cloud GPU instance. So like what I do, I rent the service from Novita AI platform, which offers on-demand CPU rental with prices ranging from 0.21 to 2.89 per hour, depending on the specific requirements. So in this demonstration, you can use the 4090 24 GB environment, which is enough for run this application. So just to pick up the server, by find your preferred region and simply deploy it with one click, and you will have a GPU instance with SSH connection ready in minutes, just like me. This one is running, and you can find the connect to see its connection string. And don't forget to set up your TCP port mapping to make sure your WebSocket port has been exposed with an external port. Here, my internal port set up in the code is 9073, and the external has been mapping to, so you can connect this web server from the internet by using this port. And it's also easy for start and stop the server for the time you actually use, which is a very flexible and budget-friendly option for experimentation and deployment. With the environment ready, now you can run your main Python code. When start, it will download the models, including the checkpoint shots, and all these models ready. The WebSocket server is running on 40 and 9073 port. If you run the service on Novita AI, don't forget to map this port to an actual external port. Again, all the source code for this project is available in my GitHub repository. I encourage you to download it, experiment with the different models and configurations, and adapt it to your own specific needs, including your front end and other apps. Leave your comments. Thanks for watching. I'll keep you updated in the next video.